negative of square root 3.5 squared would also be 3.5, and we're looking at x equal to negative 2, x naught equal negative 2. So let's look at the situation for taking the negative square roots. That would be negative square root 4.5 less than negative square root x squared less than negative square root 3.5. Okay, now the negative of the square root of x squared for x naught equal negative 2 will give us negative 2. And so this is an interval which contains our x naught equal to negative 2. And so that's the solution we want to look at. In effect, negative square root 4.5 less than x less than negative square root 3.5. Well, here what we need to do is a computation, and if you do that you'll find negative square root 3.5. Well, that's about negative 1.87. It's actually a little more negative than that, and square root 4.5 is about 2.12, so this is about a negative 2.12. So the x's that we want to consider are roughly between negative 1.87 and negative 2.12. And so if we want to be sure that our delta is going to be good enough, if we were to take delta equal to, say, 0.1, our center now is negative 2. Concentrate on that negative 2 for a second. If I subtract 0.1 from negative 2, I'll only go back to negative 2.1, which is not this far to the left. And if I add 0.1, I'll go up to negative 1.9, which is not as far to the right as negative 1.87. So in this case, we can see that delta equal 0.1 will actually work for us. That is, in the case where I take delta equal to 0.1, if I require 0 less than x minus x naught, an absolute value be less than that delta, then our f of x minus L, an absolute value, will be less than epsilon. Now let's look at a problem where we actually prove a limit. Here we want to prove the limit as x approaches 1 of f of x equal 1 if f of x equal x squared for x not equal to 1 and f of x equals 2 when x equals 1. Now notice what's happening here. Our graph of the function is just a parabola almost. There's a parabola. Notice the parabola goes through the point 1, 1. That's the curve y equal x squared. But I've drawn a little circle there to indicate that that point isn't on our graph, because for our function, when x equals 1, f of x equals 2. Okay, now remember what we said is that if you draw a vertical line over this x equals the x limit value here of 1, draw this vertical line and just cover up, we now no longer know what specifically happened at x equal 1 as far as the function is concerned, because it doesn't matter. Remember, in the definition of limit, it's 0 less than x minus x naught, which in this case is 1, being less than delta implies absolute f of x minus the limiting value, which is also 1 here, less than epsilon. In other words, this is what we need to show. And what is it that we need to show? We need to show that for every positive epsilon, such a delta can be found. In other words, that delta will be depending on epsilon, and we want to find its explicit dependence on that epsilon. So that's our problem. And notice that because 0 is less than the absolute value of x minus 1 less than delta, that means that x is not equal to 1, and so this f of x right here is x squared, no matter that f of x at x equal 1 is 2. And so consequently, when I go to solve this inequality, here I'll be replacing the f of x by x squared, even though f at 1 is 2. So let's begin by looking at our inequality involving epsilon. Our inequality now is simply absolute value of x squared minus 1 less than epsilon. And what we can notice right off is that x squared minus 1 factors as x minus 1 times x plus 1. And so consequently, we can write absolute value of x squared minus 1 less than epsilon is the same as the inequality absolute value x minus 1 times absolute value x plus 1 less than epsilon, because, of course, the absolute value of a product is just the product of the absolute values. Now you can see we could solve our inequality for what we like right away. We could write absolute value of x minus 1 is less than epsilon divided by the absolute value of x plus 1. The problem is we're not allowed to have our delta depend on the x itself. It can only depend on the x naught, which in this case is the number 1. So consequently, we have to figure out, well, how small could this get? What is it that makes epsilon over absolute x plus 1 get small? It would be the denominator getting big. So now the question is, how can we control absolute value of x plus 1? That's the question. Well, one thing we can remember is that when we're taking the limit as x approaches 1, we're making x get near 1. So why not write off, just require that the absolute value of x minus 1 be less than 1. That means whatever delta we finally choose, we'll just make sure that it's less than or equal to 1. Now, what can we say about absolute value of x when x can be at distance at most 1 from the number 1? Well, notice if x can be at most distance 1 from the number 1, the biggest x could be is 2, and so consequently the biggest x plus 1 could be is 3. And so that guarantees that absolute x plus 1 is less than 3. So what we can say then is that epsilon divided by 3 is less than epsilon divided by absolute x plus 1. And so here's the way we reason. If we require that absolute value of x minus 1 be simply less than epsilon over 3, then that's going to guarantee that it's less than epsilon over absolute value x plus 1, provided we've also required that absolute value x minus 1 be less than 1. And so that tells us what to do. We take delta to be equal to the minimum of the numbers 1 and epsilon over 3. So no matter what epsilon I'm given that's positive, if epsilon over 3 is bigger than 1, just choose delta to be 1. If epsilon over 3 is less than 1, choose delta to be epsilon over 3. In that case, if 0 is less than absolute x minus 1 is less than our delta, then this inequality holds, and so consequently this inequality holds, and therefore our original inequality holds. And so consequently we found a way to get the delta for every epsilon.